In this video, we discuss learning outcome number 2 from lesson 8.3, which is about testing a claim about a mean when the population standard deviation is known. It's also about how to handle the situation when that sample size is less than 30 and the original population doesn't seem to be normally distributed. I want to give you some options so that you are aware of how we can test claims about a mean in those special cases. So I just want you to know that when we're using or when we're testing a claim about a mean and the standard deviation of the population is known, we're basically doing exactly the same thing as we did in 8.3, except the test statistic is different. If we know the population standard deviation, then we're going to use the test statistic Z from that standard normal distribution corresponding to the sample mean rather than the student t distribution. So we're just going to use this formula. We've got, we're converting this X bar, that's our sample mean, to the corresponding Z score, which is a number of standard deviations above the mean. And in order to do that, we're going to take our X bar and we'll subtract the mean of the sample means, which is actually equal to the population mean, which will be the value of the population mean that we're assuming in the null hypothesis. And then we'll divide by the standard deviation of that distribution of sample means, which turns out to be the standard deviation of the original population divided by the square root of the sample size n. So we'll use this formula in order to get our z-score, and that z-score is a test statistic which tells us how many standard deviations above or below the mean, or the mean of the sample means, that X bar is. And then we can find p-values associated with that with the p-value method. Since we're using a standard normal distribution, we can just use our table of z-scores. You get your positive z-scores and your negative z-scores in table A2, or you can use technology to find the p-values. And we can use technology or a standard normal distribution with table A2 to find the critical values as well. Okay, so we're going to do one example. The problem statement says female dates made attractiveness ratings of men that they met when speed dating. The summary statistics are n equals 199, so there were 199 ratings. The sample mean of the attractiveness ratings of these men was 3.91. Wow. And the sample standard deviation is 0.53. So I guess these female dates did not find the men particularly attractive. I wonder if this is on a 10-point scale. I'm actually not sure. And then it says, use a 0.01 significance level to test the claim that the population mean of such ratings is less than 7, assuming that the population standard deviation is 1.99. Now, the fact that we know that the population standard deviation is 1.99 is pretty unusual, but we're going to assume it for this problem so that we can practice testing a claim about a mean in the case when the population standard deviation is known. The first thing we do is we check the requirements. First, we would assume that we have a simple random sample and our sample size is 199. We've got 199 ratings, and the sampling distribution of the sample means will be approximately normal. Okay, now that we have checked the requirements, we know that we can use the methods that we've previously discussed. So we're going to state the claim in symbolic form and use it to infer the null and alternative hypotheses. So I go up to my problem statement and I'm looking for the claim. It says use a 0.01 significance level, to test the claim that the population mean of such ratings is less than 7.00. So the mean is less than 7.00. That is our claim. Now, since it has a strictly less than sign, that's our alternative hypothesis as well. And to get the null hypothesis, we just change that less than sign to an equal sign. Okay. After you've got your null and alternative hypotheses, you want to identify all the important information that will allow you to compute the test statistic. So we need to identify the sample size, the sample mean, and sample standard deviation. And actually, they're all listed for us right there. So n is equal to 199, the sample mean is 3.91, and the sample standard deviation turns out to be 0.53. And then we want to think about whether that 3.91 is significantly low, given that the null hypothesis is true. And the null hypothesis is that the true population mean is 7.00. So that's saying that the true mean rating of those women for the men that they are speed dating with, the mean attractiveness rating of the women about the men is 7.00. So we're saying, okay, if the mean is 7.00, how extreme or how rare is it to get a sample mean of 3.91? Is that significantly low? If it is, we can throw out the null hypothesis. We can say if something that is supposed to be rare is happening and it's happening frequently, well, then maybe the underlying assumption that leads us to believe it is rare is false. And our underlying assumption is that the null hypothesis is true. Now, in order to answer this question, the question of whether or not this x bar equals 3.91 is significantly low, given that the null hypothesis is true, we need to convert that x bar to a test statistic. Since we know the population standard deviation sigma, we can use z-scores rather than t-scores. So we're going to convert from this distribution to a standard normal distribution. So we're saying if x bar equals 3.91, what's the corresponding z-score? How many standard deviations below the mean is this 3.91, provided the actual mean is 7.00? In order to do that, we're going to use this formula. So we're just using the formula to convert from a continuous random variable, a normally distributed continuous random variable, back to the corresponding z-score. Except instead of using x for a continuous random variable, the continuous random variable in this case is x bar. That's the sample mean. So we're taking the sample mean and we're subtracting the mean of the sample means, and then we're dividing by the standard deviation of the sample means. And the mean of the sample means, we know from 6.3, is equal to the true population mean. And the population mean is assumed to be 7.00 in this case. And we're saying, if that's true, how many standard deviations is this 3.91 below the mean? So we substitute the value of the population mean from the null hypothesis. In the denominator, you've got the population standard deviation, which was given to us to be 1.99. And then we divide by the square root of the sample size. That turns out to be the standard deviation of the sample means. So we get that, and we get the z-score of negative 21.9044. That is low, very, very low. This graph is grossly wrong. It looks like from the graph that my test statistic z is about negative 1.3 or negative 1.4. This is actually 21.9044 standard deviations below the mean. So it's way, way, way out. Very, very low. So that is significantly low. So I think we're going to reject the null hypothesis, but let's go through the rest of the procedure to do that as we usually do. Okay, so now we're going to make a decision about the null hypothesis. One way that we can do that is using the p-value method. Now, whenever you're using the p-value method or the critical value method, you need to determine whether the test is left-tailed, right-tailed, or two-tailed. And the way we do that is we look at the alternative hypothesis. So the alternative hypothesis in this case is that the mean is less than 7.00. Since that's a strictly less than, that is a left-tailed test. You can think of that as an arrow pointing to the left, so it's a left-tailed test. And then we said, okay, we got this test statistic of negative 21.9044. If we have a left-tailed test, the p-value is the area to the left of z equals negative 21.9044. So there's not very much area over there at all. In order to find that area, you can either use Excel or table A2. Using table A2, we get a p-value of 0.01. So this is my table of negative z-scores from the Triola formulas and tables. And since my value of z was negative 21.9044, I go over here and I'm looking for the lowest z-score on the table. Notice that the lowest z-score on our table is just this z equals negative 3.5. So we're saying if z is negative 3.5 or lower, we're going to assume that the area to the left is this area, which is 0.0001. For practical purposes, we're going to say that the p-value is equal to that value. But our p-value is actually going to be much less than that. Because let's look at our graph again. Whoops. We're talking about the area to the left of this z equals negative 21.9004. And this is z equals -1. There's -2, -3, -4 would be over here, -5, approximately there, -6, -7, -8, -9, -10, -11, -12, -13. See, I'm not even going to get to 21. There's like 22 standard deviations below the mean. It's way, way, way out there. And remember, this whole time, as you go farther and farther out, this tail is getting smaller. It's not crossing that axis. I'm not very good at drawing this with my mouse here, but the idea is that tail is getting longer and longer and it's closer and closer to that axis. And the p-value is the area under the tail. So it's tiny, very, very tiny. The area to the left of z equals negative 21.9044 is so small that Excel might not even find a value for us. So if we wanted, we could use Excel for this, and that would be fine. That would be a great approach as well. Sorry, I'm trying to get my mouse to appear again. There we go. So let's look at Excel now. If I'm in Excel and I want that p-value, I've got to use the norm at .s .inverse function. Oh, actually, no, I don't. Just kidding. That's where they're asking for a probability, and then you give them a probability and they're asking for a z-score. We want to go the other way. So I want the norm.dist. That's right. And so we would type this negative 21.9044. We said we've got a mean of 0 and a standard deviation of 1. And yes, we want the cumulative area to the left. Oh, okay, we actually get a z-score or a p-value. I don't know if you know what that means. That's 1.179 times 10 to the negative 106. So that is 0.0000. And I'm going to have to say that 000. I'm going to have to add 105 zeros, and then we'll have the 1179. Tiny, tiny, so much tinier than 0.0001. That's 10 times 10 to the negative 106. So I want you guys to see how small that is. Like, there's so many zeros, 105 zeros before we get the first significant digit of the number that's non-zero. So the p-value is just ridiculously small. Okay, so we can use this function and we get this very, very tiny number. And obviously this tiny number or this tiny number are both smaller than the alpha equals 0.01 significance level, since that probability is very tiny. This is the probability of getting a x bar equal to our x bar, or an x bar that is even less than our x bar, is 1.1 times 10 to the negative 106. It's just a minuscule probability. So that would be just ridiculously, I'm using the word ridiculous wrong. It would be just extraordinarily rare to have that happen if the null hypothesis is true. So we're going to say, well, maybe if this is actually happening, and it's supposed to be this rare, because we're assuming that the null hypothesis is true, maybe that assumption that the null hypothesis is true is wrong. So we're going to reject the null hypothesis. Again, that's just another application of that rare event rule that we talked about at the beginning of the semester. So we're saying that tiny, tiny area to the left of z equals negative 21.9044 is that, and that area corresponds to a probability that would happen given that the null is true. So the null must be false. Okay, that's one way of doing it. That's the p-value method. Another method is to use the critical value method. So we still have to check and see what type of test we have. We look at the alternative hypothesis, we see that we've got a less than sign there. It's like it's an arrow pointing to the left. So we're going to use a left-tailed test. For the critical value method, and we need to find the significance level alpha. So the significance level alpha is 0.01. So when we find our critical value, we want a z-score that will give us an area to the left of 0.01. So we're going to our table of values and we're looking in the body of the table for a probability or an area of 0.01, and then we want the corresponding z-value. So if I want a tiny probability of 0.01, I'm going to the negative z-scores table. I'm looking in the body of the table for 0.01, or as close as I can get to it. There it is. That is as close as I can get. This one is also pretty close, but this one is off by 0.0002, and this one is off by 0.0001. So the corresponding z-score is z equals negative 2.3, and then this is the this column, the one with the 0.0099 in it, corresponds to that 3 in the hundredths place. So this is z equals negative 2.33. So that's what we get using table A2. Or if you wanted to, you could use Excel. Let's go to Excel and show that how we get that now. Here is where I have the probability, the area to the left, and I want the corresponding z-score. So this is where I will use that norm.s for standard normal distribution inverse. Giving them a probability of 0.01, I want the z-score. And so they give us this, negative 2.326. And then if we round to 2 decimal places, we see that we get the same value that we had in our table A2. So either way, you're getting the same answer. Okay. And so that is giving us this z-score here, this critical value of z, and the area to the left of that is 0.01. And so then we say, okay, where is the test statistic relative to this? Well, remember our test statistic was negative 21.904. So our test statistic is like way out here. So I'm going to say way out here. It's far out in that left tail. Since that test statistic is in the critical region, we reject the null. Or alternatively, you can look at it this way. You can take the absolute value of that negative 21.904, get positive 21. And that's going to be greater than the absolute value of the critical value of z. The absolute value of that negative 2.33 is 2.33. All that inequality is saying is that that test statistic is farther out in the tails than the critical value is. So that means we will reject the null hypothesis. Okay. All right. So using the p-value method, we decided to reject the null. Using the critical value method, we decided to reject the null. I'm not going to do the confidence interval method here, but you'll get the same results using the confidence interval method as well. We're going to reject the null hypothesis. That x bar of negative or positive 3.91 is extraordinarily rare if the null hypothesis is true, that the true population mean is 7.00. So we're rejecting the null hypothesis. And this time the claim was the alternative hypothesis. So when we reject the null, we're actually supporting the claim. So this is how we'll state our conclusion in non-technical terms. We're going to say there's sufficient evidence to support the claim that the mean rating of females of their speed dating partners is less than 7.00. So this method you see is just like the method that we looked at in the last video. The only difference is that we're using the standard normal distribution to compute our test statistic and our corresponding critical values and the corresponding p-values or the probabilities. but it's all the same as what we did last time. The only difference is we switched out that student t distribution for the standard normal distribution. Now, if the population that we are pulling from is not a normally distributed population, and the sample size is less than or equal to 30, then you do have some other options. Now, I'm not going to go over those options in too much detail because we just don't have time in our course. But I want you to be aware of the fact that you can still test a claim about a mean in those cases. Here are some options for you. So one option is to use what's called bootstrap resampling. This is described in more detail in 7.4. Due to time constraints, we did not cover 7.4, but you can go back and review that if you need to test a claim about a mean and you have evidence that suggests that the data comes from a population that's not normally distributed, or and you have a small sample size at the same time. So go back to 7.4 if you need to and study that bootstrap resampling. This will, when we're testing a claim about a mean in this case, we're going to use the confidence interval method, but we have to obtain the confidence interval using that bootstrap resampling, sorry. Another option is what's called a sign test. This is covered in section 13.2 of another book by Mr. Triola called Elementary Statistics. Our book is called Essentials of Statistics, but Mr. Triola wrote another book that has more chapters. In chapter 13, you can learn about how you handle this case using what's called a sign test. And there's also the Wilcoxon signed ranks test, which is also in section 13.2 of that other textbook. So I want you to know, if the population is not normally distributed or you have a small sample size, there are options. We're just not covering those in our course. If you need those options, those can be easily found by looking up resources. You can go back to 7.4 and learn about how to handle that case using the methods described in our textbook, or you can just find another textbook. Find this elementary statistics textbook by Mr. Triola, and he's going to give you some options, these last two options that will allow you to handle this as well. So that's it. That is the end of our discussion of lesson 8.3. I will see you next time to discuss hypothesis tests about more than one proportion or more than one mean in chapter 9.